So my name is Pablo Piskunov. I will tell you about the kernel polynomial method implemented into Quant. So I know almost everything that is here because I mainly wrote it with a lot of help from Anton, also Joseph, Weston, Daniel, and many more Quant contributors. Let me fix one Zoom. 1 second. No. Okay, so this is the outline of this very quick talk. I will introduce the KPM expansion of a function, then how this applies to a spectral operator. In that form, we will get the spectral densities. And then we will play around a little bit with the capabilities added into Quant, such as improving the kernel polynomial approximation by adding moments or adding vectors. Later on, we will see how the vector factories work and why do we need them. And finally, as a nice application, we will see how to compute the Kubo conductivity in the Kubo-Bastien expansion, which is already implemented into Quant, but of course there is a bit of extension that can be done. So this will be left as an exercise. Okay, so let's dive into it. The notebook has a bunch of references, so if some part is not clear and later on you want to study this and see how it works, please check the references, which are very, very useful. So,
Pablo,
yes?
Could you zoom in a little bit? People.
Yes, sorry.
Thanks.
How about now?
That's great. Yeah. Okay,
great. So we'll start with a KPM expansion. So basically, this is based on a polynomial expansion of simple functions. Simple or complicated, it doesn't matter. This works very similar to Fourier expansion, where you have some polynomials or some base functions, and you get some coefficients that multiply these base functions, and then you have an approximation of your function. Right, so in this case, it's done by polynomials, which have this very nice recursion relation. So the first polynomial is just the unity. The second is just the identity, so it's x. And then there is a recursion relation to get the polynomial number 2 and 3 and so on, which is multiplying 2 times x times the previous polynomial minus the previous polynomial. So it's very, very simple. And if you have any function defined in some finite interval, you can rescale this function to the interval -1 to 1 and expand this function f as a sum of coefficients times the Chebyshev polynomials t sub n. Of course, these coefficients comes from the inner product defined by the polynomials, which is basically the integral of your function with a set polynomial of order n. So you get mu sub n, and in the KPM lingo are called the moments of the expansion. So very nice, we have a polynomial approximation for any function in some finite interval. And since tight binding systems have a spectrum defining this interval, this looks very appealing. So what we will do is now look a little bit into spectral densities. So a spectral density is just the spectral weight that some operator has on your system. So the easiest example of this would be the density of states. So the density of states is just a collection of delta peaks for a finite system, a closed finite system. It's a collection of delta peaks each of these delta peaks appears on one possible energy of your Hamiltonian. So usually to solve the Hamiltonian, you get the eigenvalues. You know, H applied to an eigenvector k gives you E of k times k. And the spectral density you could define as the delta function of the Hamiltonian minus some energy variable. And the spectral density, rho of E, which is the density of states of the delta function, is just the trace of this operator here. So since we want to expand this rho of E, we will compute the moments, the coefficients of my expansion. And if you do the math, you will realize it's just Tn of each value of E of k. Now you can remember that a function of an eigenvalue, it's just applied to some eigenvector. It's just the function applied to the Hamiltonian. So this gives you an operator. So you can see, if you follow the math, you can see that the moments mu sub n is just a trace of the Chebyshev polynomial of order n applied to the Hamiltonian. So this object here can be quite hard to compute because it's a polynomial on a Hamiltonian. It gets very dense. But if you express it like this, it's actually very easy to compute, and we resort on the recursion relation to compute it much faster. So let's dive into the Quant implementation. I will make a quick example using, again, graphene, because graphene is the new square lattice. I mean, it's the new standard for having system that looks more or less interesting. So first of all, I defined some hopping kinds just because later on I want to define the Haldane model and Kernel model, and I need these hoppings in the right order. So we can execute all this. Then I define my system. We'll make a graphene system of some radius. I will define some first neighbors hopping and second neighbors hopping. Usually this will be 0 unless I will explicitly say otherwise. So I make my lattice and list of neighbors. I get my builder. I define a shape function, which is just the length of this vector position should be smaller than the radius. So I will make a disk. And I create the sides of my system inside the disk. I say that all the hoppings inside this system are unit hoppings or value t. And then I check if there is a non-zero t2 value, there will be second neighbors hoppings. And then I just finalize and return the system. Then I have some function to plot the spectrum. I will tell you in a minute what is this spectrum object here. But basically, I will be plotting the energies and densities of my spectrum. So let's check how it works. I make a graphene system, radius 20 unit cells, lattice constant, sorry. And then I simply call Quant KPM spectral density. And this returns a spectrum object. So we will see what we can do with this spectrum object. First of all, this contains energies and densities attributes inside, which if you plot them, you get these, which in a really blazing fast time, you get something very, very nice and that looks like the density of states. So it's kind of wiggly, it's kind of noisy, it's not very sharp, and we will see in a minute why this happens and how to make it better. So there is two things that I didn't speak about yet, which is the energy resolution, which means how sharp these features that appear here should be. So this is ultimately dictated inside the spectrum by this parameter, num moments, which is just the order of my KPM expansion. So I print the number of moments before, then I call this method add moments. By default, I had 100 moments. Then I added 300, so now I have 400. And adding these moments made the KPM module to compute much more expansions, much more orders in my KPM expansion. So now you can see that if you plot the spectrum, you get much sharper resolution. You can see many peaks that corresponds to states in my finite system. And the spectrum object comes also with some other convenience functions, such as the integration, which is done very fast inside the KPM module. So the integrate method, what is trying to do is to get some, for example, let's say that you want to compute the number of field states below some Fermi energy. Then you compute the spectral density or the density of states times the Fermi distribution function at this energy. And you can do it like this. So I pass here a zero temperature distribution function, which means this function lambda E will return 0 if the energy is above the Fermi energy and 1 otherwise. So I get some number. It's not really even number. It's not a round number. And I will tell you in a minute why this happens. But it's fairly close to half the number of half the number of total states or total number of orbitals in my system, which is what we expect.
Pablo, sorry, I'm looking also a bit at the time here. You have like 1 or 2 minutes or so.
So I will skip the effect of temperature. I will dive into the vector factories. So please check the notebook that will be available to use to play around with it. If I add random vectors, I get a more even spectrum. Let me go quickly over the vector factories. So you can define areas where the vectors that you use for your KPM expansion are defined. For example, here I only take the bulk of the system and not the edges. And then this little peak that was at 0 disappears, which is something coming from the edges of my disk. And I get a much cleaner sample if I take just one unit cell in the middle of my sample and no random vectors. Finally, I want to show the Kubo conductivity, which you can check the implementation here. I make a non-trivial system. I put T2 hopping, so I have a Haldane model. I have to take care of the normalization of the output of the conductivity. And finally, I can compute the sigma xy, which is the Kubo Hall conductivity. And I see that inside the gap that I define in my topological system, inside the gap, the conductivity is quantized, perfectly quantized to the value of 2, which is what we expect. And well, that's all. Then there are some exercises. There is a very easy one and a fairly hard one. So please check them out. And there are also some references. Thanks for your attention.